Section 2.1, Interior enclosure of sets. Definition 2.1. Let A be a subset of a topological space X. The interior of A, denoted A circle or int A, is the union of all open sets contained in A. So it's the largest open set inside of A. The closure of A, denoted A bar, or CL of A, is the intersection of all closed sets containing A. So it's the smallest closed set containing A. Well, exercise 2.3 is going to refer to the digital line topology, which we saw back in chapter 1. So you can recall that it has a basis consisting of singleton sets at the odd integers, and then sets of 3 consecutive integers centered around the even integers. So to get the open sets of the topology, we take arbitrary unions of these basis elements. Now, exercise 2.3 says, for m less than n, both integers, let I sub mn be this digital interval consisting of just the integers from m up to n. And we're supposed to determine the interior enclosure of I sub mn in the digital line topology. Okay. Well, before we try and write down the answer, it's convenient to extend this IMN notation for digital intervals to include more cases. The first one, we can let m and n be equal to one another, in which case we just get a singleton set. We can let the left endpoint be negative infinity, in which case we get all integers less than or equal to n. Similarly, we can let the right endpoint be infinity to get all integers greater than or equal to m. And if we let both endpoints be infinite, then we just get all integers, which is the same thing as the set Z. Okay. Now, in order to talk about interior, we need to know what the open sets are in this topology, and in order to talk about closure, we need to know about the closed sets. So, let's see. Open sets are arbitrary unions of these basis elements. And if you think about it, when you take unions of those, then you're just going to end up with a bunch of digital intervals, and they're all going to have odd endpoints, right? You may have some singletons in there, which we now have a notation for. If you take sort of an infinite number of them and take the union of them going off in one direction, you may get one of these infinite intervals, or maybe even all of Z. But we can summarize all of that by saying that these are unions of digital intervals of the, let's just say I sub mn. We have this notation for it. With m and n either odd or infinite. Okay. And of course, a union could be the union of nothing, in which case it would be the empty set, and that's open, as it always is. All right, and then the closed sets are the complements of these open sets. And if you think about it, if you have the set of integers and you take out a bunch of sort of intervals with odd endpoints, then what's left are intervals with even endpoints, or maybe infinite endpoints again. So we can say, well, we can just copy what we've written up here and change that word odd to even. Okay. Good. Well, now let's see what we have here. So in our original situation where m is less than n, for interior we have 4 cases, depending on whether m and n are odd and even. And in the case where m and n are odd, well, we've just said that such a digital interval is open already. Okay, so it itself is the largest open set contained inside of itself. Okay, so the interior of IMN is equal to IMN. Now, if m and n are both even, then to get an open set contained inside IMN, we're going to need to get rid of those 2 even integers in the end, the 2 ends of the interval. Okay, so that we instead are taking the interval from m plus 1 up to n minus 1, both of which will be odd. Okay? And so that's the interior in that case. And if m is odd and n is even, then we can leave m as it is, but we need to shave off the n, so we get n minus 1. And if m is even and n is odd, then we need to move the left endpoint 1 to the right. Okay, so we have m plus 1 and n. And then for the closure, we are looking for closed sets which have even or infinite endpoints. And all right, so if m and n are odd, then we're going to need to move each of those endpoints out by 1. Right? Move the left endpoint 1 to the left to m minus 1, and the right endpoint 1 to the right to m plus 1, so that we end up with even endpoints and get a closed interval. That'll be the smallest closed set containing imn. And okay, if m and n are even, then we already have a closed set, so we just get imn again. And in these last two cases, we have to take the odd endpoint and move it out 1. So in this case, m moves to m minus 1. In this case, n moves over to the right to m plus 1. And that does it. One interesting thing to notice here is that in each of sort of the 4 cases, the interior is never equal to the closure. It's actually a proper subset for this particular topology. Okay.